All right. Welcome everyone to the November 2023 COMSOC seminar. Today we have two speakers who are going to speak about some new ideas in social choice that they are going to show you applications of these ideas in certain domains. But pay attention to these ideas because you can take these ideas and you can apply them to a bunch of other social choice problems. And indeed, the literature on both these ideas, which is learning augmented mechanism design and distortion, they have both been applied to a whole bunch of social choice problems already. Okay, so it's my pleasure to first invite Vasilis Gkatzelis, who is from Drexel University, to talk about learning augmented mechanism design.
Thank you, Nisarg. Let me just share here. Okay, great. So yeah, let me start by thanking the organizers for the invite and all of you for attending. And I want to start by saying that I've only given longer versions of this talk. It's the first time I'm giving a 20-minute version, but I'll try to convey the main portions of the model that I think are interesting, and maybe you can take away from this and try to apply in your own problems. But also, there's a question session afterwards. I can talk more about the actual applications if I don't have enough time, so feel free to ask afterwards. So this is about learning augmented mechanism design, leveraging predictions for facility location. This is joint work with Eric Balkansky, Priyank Agarwal, and Tingting Wu from Columbia University, and my PhD student CJ Tan from Drexel University. And let me start by just talking about learning augmented algorithms before I go into learning augmented mechanisms. So the point of this model is to address the tension between worst case analysis of algorithms, what is the classic approach of analysis of algorithms in computer science, and the fact that machine learning algorithms have been becoming more and more prevalent. So on one side, we have worst case analysis, which provides robust guarantees. We know that whatever worst case analysis guarantees, it's always going to be true, but often it's too pessimistic. So it doesn't tell us as much. It tells us it's definitely going to be true, that guarantee, but it might not be that optimistic. On the other hand, machine learning algorithms seem to work well in practice, but lack robustness. We cannot really necessarily trust that they're always going to perform well. So this line of work on learning augmented algorithms tries to enhance algorithms, go one step further, and rather than throw away worst case analysis and all its benefits, the point is to keep worst case analysis, the benefits of that, and maybe also incorporate the benefits of machine learning algorithms and try to get the best of these worlds. So traditionally, in algorithm design, what we think of is we have a problem instance coming into the algorithm and the output, and that gives you a particular output, and you can try to evaluate the performance and the value of that output in a worst case sense. What's the worst that could happen? So a learning augmented algorithm, instead, what it does is it's given, think of exogenously some machine learning algorithm, some group, some people have done some work, some priors. You can use whatever information you like to then develop some prediction over something that's relevant, that could really be helpful if that was correct. So you get this machine learning advice or prediction. And the thing is that it could be incorrect, that it's untrusted. You cannot really trust it to be true. It's a signal. Someone says, I think that's what's going to happen, or I think this is where you should aim to direct your algorithm toward that. So you don't really want to trust it. You don't want to depend on it too much. But the goal here is going to be, well, if it's true, though, maybe we can still do better. So the goal is going to be to maintain worst case performance. But if this untrusted prediction that we get as input is actually correct, now we demand more of our algorithm, that it does well condition for whenever this prediction happens to be correct. So an ideal algorithm with prediction would be what? Would achieve the optimal worst case performance guarantee, whatever we knew was the best we can do in a worst case sense, while at the same time saying, if the prediction is optimal, I'll give you the optimal solution. Where the prediction is correct, I'll do amazing, right? So not losing anything, we still maintain the worst case performance, but at the same time, if it just so happens that the prediction we got is correct, we guarantee something much stronger at the same time. Of course, that might be impossible in some settings, right? The only way to really hope for very good performance, for consistency, for what is known as consistency, very good performance, assuming the prediction is correct, is to lean on it a little bit too much, in which case we sacrifice worst case performance, right? We trust the prediction. So there's often a trade-off between the two. So prior work in this literature has introduced two different measures to evaluate, essentially it's by criteria guarantee. So we're on they call robustness what was traditionally called worst case performance. So meaning your robustness of an algorithm is what is its worst case performance guarantee? And consistency is what is its performance guarantee, assuming the prediction is correct, right? And the goal is to understand now, do we need to trade off one for the other? Can we get the best of both worlds? Can we get the best robustness and the best consistency at the same time? Or do we need, in order to get consistency, meaning again, a good performance, assuming the prediction is accurate, do we need to sacrifice robustness in order to do that, right? And in different problems, sometimes we need to trade off one for the other. Sometimes it actually happens that we can get the best of both worlds. And I'll try to give instances of that in facility location that hopefully many of you relate to. So this is a very vibrant literature. In the last 5 years alone, there has been more than 160 papers. There's a website that I recommend. If you search for algorithms with prediction website, you'll see all these papers organized by theme, by is it algorithmic game theory? Is it online algorithms? Is it data structures, running time? What's the theme, the application of it? So there's many, it's organized very well and it's updated frequently. So I do recommend if you're interested in this literature to see there for an organized, structured way of viewing prior work. So the novelty in what we do here in this talk and subsequent work that I'll just list at the end of my talk is we actually adapt this setting to strategic settings or multi-agent systems. So you have multiple agents, and we talk again about robustness and consistency, essentially in social choice settings, potentially also including strategic agents, right? So then again, you can talk about evaluating voting rules or evaluating mechanisms and auctions in the worst case sense, as traditionally a lot of computer science literature does. But sometimes when this is a little bit too pessimistic, maybe you can say, what if I'm given some prediction, some untrusted prediction? Can I do much better if this is the case, if the prediction happens to be accurate? Again, without sacrificing too much robustness, not throwing away worst case analysis altogether. Okay. So let me jump in and instantiate those on the facility location, strategic facility location problem. Hopefully many of you know this already, but let me introduce it. So we're going to be talking about Euclidean space. So we want to locate in a single facility in Euclidean space. Each agent I has a preferred location in that space. You can think of it as just one dot, like one block dot in this Euclidean space. And we need to choose one facility in that same space. Let's say we choose this green star. Then once we do that, the cost of each agent I is a Euclidean distance from their preferred location to the chosen facility location, right? And then given the setting, so our outcome space is the set of facility locations. The performance is going to evaluate it by different social cost objectives. So the obvious ones are the ones that we're going to consider. One is egalitarian social cost. Our goal is going to minimize the maximum cost over all the agents. So given a facility, everybody suffers a cost. What's the maximum? We're going to try to minimize that. The other obvious one is the utilitarian social cost. So we're going to try to minimize the average social cost, the average cost over all agents. So the mechanism design aspect to this is, well, what if the locations, the preferred locations of the agents are private? We don't really know them. You cannot verify them. So we need them to report what their preferred location is. And therefore, and they can be strategic, meaning they can lie about this if that actually benefits them. So once we publish how we're going to aggregate these preferences, they can strategically misreport the preferred location if that actually leads to a facility that they prefer, a facility location that they prefer. So we're going to have to aim for strategy proof or truthful mechanisms where under no circumstances does any agent want to actually lie and misreport. So since just choosing the optimal facility F star, optimal facility location F star is not strategy proof. We'll see examples where this is not. We cannot just hopefully just output the optimal and assume people are not going to lie. This is not the case. If we select F instead, some suboptimal one, we're going to evaluate it using worst case approximation, right? So the maximum over all possible instances of the social cost in what we return divided by the social cost of F star. So how many times worse is the social cost in the worst case possible instance? And that's going to be our robustness. The robustness of a mechanism is going to be over all instances. What's the worst performance that it achieves? Consistency is going to be, given some prediction regarding this instance, how much better can you guarantee? Well, how much better is this going to be, assuming the prediction is correct? So there's going to be a trade-off between the approximation guarantee you can give in the worst case and the approximation guarantee you can give, assuming the prediction is correct. And hopefully, at this point, you're wondering, what is the prediction, right? And that's an interesting question, because that's an open-ended one. Different settings, you can come up with different predictions. You can argue what is interesting, what will be natural, what should we expect a machine learning algorithm to try to at least approximate, right? So let's, as a warm-up, start with facility location on the line. So just to give you kind of already the answer to what we're going to be doing, the prediction is going to be over where that green star is. The prediction is going to say, I believe someone's going to exogenously tell us, here's where I think the optimal location is, right? And that's a prediction, again, that could be totally untrusted, that cannot be trusted, so it can be totally wrong. I'm going to try to use that signal, though, to maybe do better if that prediction is actually accurate. Okay. So before I do that, let me just, as a warm-up, start with facility location on the line before we go to the Euclidean 2 dimensions. So let's first consider utilitarian social cost. So for this case, if we want to minimize the average, the optimal thing to do is return the median. So if we take all the points, return the median, it's easy to verify that that actually is the optimal. It just so happens, in this case, that's also strategy proof, right? So actually, in this case, people would not lie. If everybody reports their location on the line and we return the median, that actually is going to be a strategy proof mechanism. We can discuss later if you're not aware of that result already, but this is true. Trust me for now. On the other hand, if you want to minimize the egalitarian social cost, what you would want to do is to take the leftmost, the rightmost point, and find the average of the two, right down the middle. Because these extreme points, the leftmost and the rightmost, are going to be the ones that suffer the biggest cost. So you want to split that cost to minimize the maximum. In this case, if you were to just say, everybody report your locations, I'll just output that middle point between the average of the leftmost and the rightmost, it's not going to be strategy proof. It's easy to think of examples where, for instance, the rightmost agent will just pretend they're actually further to the right, and by doing so, they will drag the facility location, the chosen facility location, closer to them, the more so they do, right? So they can lie by pretending they're more extreme, they're further to the right, just to drag the facility location closer to them and benefit from that. So this is a clean example where just hopefully returning what is the optimum is not going to be strategy proof. People will manipulate this, and this can lead to much worse outcomes. On the other hand, if you choose the median, if you just say, let's go back to what seemed to work for average, you do get a too robust strategy proof mechanism. So this is going to be strategy proof, and it's never going to be more than 2 times worse than the optimal, right? So these are, again, known results from prior work. And this is optimal. No deterministic mechanism could do better than that. No deterministic mechanism can beat 2. That's the best, even for the line, that's the best approximation guarantee that one could hope. And this is where I want to pause for a minute and say, okay, so this is the setting we described. Worst case performance guarantees, that's the best that we can hope for. 2 approximation is the best that we can hope for, even on the line, if we want strategy proofness. And the question is, can we maintain that 2 robustness, that worst case guarantee of 2, while at the same time, if we get some prediction and we trust it a little bit, try to do better without sacrificing that 2? And this is where I want to kind of briefly discuss what would be a reasonable prediction. I think most people, when they're asked what's the prediction in this setting, most people I've discussed it with at least, would say, well, the points. Where are the points? Anything that the mechanism doesn't know, let's have a prediction over where every one of these agents lie. And that would be a reasonable one. It's essentially all the information that the designer is missing. That's what we could call our prediction. Ask the machine learning algorithm to guess where everybody is, and then use those predicted points to guide us in designing our mechanism. What we do instead is something stronger. In other words, we need a weaker prediction for what we show in this talk. We just predict the optimal facility location. It's easy to verify that. If you have prediction over all the points, computationally, it's very easy from those to deduce a prediction for where the optimal point would be. The problem computationally is very easy, right? So if you know you have a prediction for where each one of the agents lie, then from that you can infer a prediction over the optimal facility location, right? What we're saying instead, though, is just give us a prediction regarding the optimal facility location. So that's just one point instead of many of them, and many different actual agent points map to the same optimal location, right? So we're asking for strictly less information, right? So it's a stronger guarantee if we can get something positive here, because we're asking for a less strong prediction. But what can we do with it, right? So let's visualize this. Here on the line, we have these points. Think of it, the input would be these points. We elicit from each one of the agents where their preferred location is. And then we get an additional red point, which is the prediction. The prediction says, I think this is where you should put your facility. Okay, but it could be also over there on the left, right? And again, it's untrusted. It could be arbitrarily incorrect. This is just a point that the machine learning algorithm said, based on historical data, this is where I think you should place your facility. What should we do, right? How can we design mechanisms that are still strategy proof? We don't want people to start lying, but might perform better if that prediction is correct. And again, without sacrificing worst case performance, ideally, even if the prediction is arbitrarily incorrect. Okay. So here's how we can actually do this. For the egalitarian social cost, trying to minimize the maximum, we can do the following. If the prediction happens to be between the minimum and the maximum reported points, trust it. Just return the prediction. Right? So given the points, everybody strategically potentially reported their points. If my prediction happens to be in the middle, so for instance, if it's like where we see the red point now, just always return the prediction. If, on the other hand, the prediction is further to the left or further to the right, just return the point that is closest to the prediction. For instance, if the prediction is always there or over there, just return the agent, the leftmost agent. Right? It's not too hard to verify that this actually remains strategy proof. Nobody will benefit by lying in this mechanism. And the question then is, and we can discuss this if you're not convinced, but under no circumstances can anyone ever benefit by lying about the location. The question is, what did we buy with this, right? Sure, this mechanism sometimes uses a prediction as a guide. So what we buy with this is that this mechanism is actually too robust, the best you could ever hope in terms of robustness, and one consistent. It means whenever the prediction is correct, it always outputs the optimal location. So it gets exactly the best of both worlds without sacrificing anything in terms of the best worst case guarantee you could hope to achieve. It nevertheless gives you the perfect outcome whenever the prediction happens to be correct. Again, it doesn't lose any robustness, even if the prediction is horrible, right? So that's the best you can ever hope for in this setting, right? So optimal consistency and robustness at the same time. That's not always the case. Usually you need to trade off one for the other. That's just a very clean example where you can get both. So to see one where you cannot get both, let's go to two dimensions, again, the egalitarian social cost. And I might not have time to talk about utilitarian social cost, but that's fine. So what we do for two dimensions, egalitarian social cost, is the following. We find the minimum axis parallel bounding box of these points, right? So the smallest box, axis parallel box, that contains all of these points. And now, if the prediction happens to be in this box, return the prediction. If the prediction happens to be outside this box, then essentially return the point of the box that is closest to the prediction, not an agent's location, a point on the box that's closest to the prediction. A different way of thinking about it is like running the previous mechanism on each dimension separately. If that you find that more convenient to think about, you run the previous mechanism on the x coordinates and the previous mechanism on the y coordinates, and you're going to get that outcome. Right? So again, the question is now in this two-dimensional space, what can we actually get? So this mechanism is 1 consistent and 1 plus root 2 robust. So this is a little bit worse. This is 2.4 rather than the 2 that we could actually guarantee otherwise. So we lost a little bit. Was that necessary, right? So this mechanism is still giving you the optimal outcome whenever the prediction is correct, but might lose a 2.4 factor whenever, if the prediction is not correct. Well, as it happens, that is the best trade-off you could ever get. So any deterministic, at least among deterministic mechanisms, any deterministic strategy-proof mechanism that is better than too consistent. In other words, so if you want too robustness and too consistency, that's easy to get, right? Just disregard the prediction. If you disregard the prediction, you're going to get a too robust algorithm. Of course, your consistency is not going to be any better than 2, right? So that the whole point is you're trying to get consistency better than 2, to beat the 2 whenever the prediction is correct. But you can always get too robustness, too consistency by forgetting about the prediction and doing whatever is the worst case optimal thing to do. So you could get that to robustness to consistency, but whenever any deterministic mechanism that tries to get any any consistency better than 2, the moment you try to get 1.99 consistency, you have to lose robustness. Suddenly there's a jump to 1 plus root 2 robustness. And we actually achieve the 1 plus 2 root 2 robustness with 1 consistency. We don't go to 1.99, we go directly all the way to 1. Okay? So these are the best 2 points you could hope for. So you can either disregard the prediction and go for 2 robustness to consistency, or 1 consistency with just the slight jump in robustness. You lose a little bit in worst case guarantee, and you get much better consistency. And just one point that I don't know if many of you are thinking about, but what if the prediction is not correct? It's just slightly off. What if there's an error? There's a distance between our predicted optimal facility location and the true optimal facility location. The previous statement makes no guarantee about this, right? It says the moment the prediction is slightly incorrect, I have no promises. I'm only promising something if it's correct. As it happens, though, we can actually parameterize our guarantees as a function of the error. So if the prediction is not fully accurate, there's an eta error in the prediction, we can get a 1 plus eta approximation. So something that when eta is 0 retrieves the 1, increases linearly. So as eta or error increases, that approximation also increases, but is capped at 1 plus root 2. It will never get worse than 1 plus root 2. So that's not just these 2 extreme points, we also get a smooth degradation as a function of the error. So as I said, I'm going to skip the utilitarian portion. I'm happy to discuss this, that we actually are based on coordinate-wise median as a base choice. So in other words, for each run the median on the x coordinates, run the median on the y coordinates. And the way we do this, the way we get our positive result, is we actually introduce phantom points. Many of you are familiar with this. That's why I'm kind of using the term. And our phantom points are the prediction. And then the main way in which we're biasing in favor of the prediction is we're adding an appropriate number of phantom points that are all equal to the prediction. So we're putting weight on the prediction by just introducing phantom points and then running this coordinate-wise median. And the main thing to remember from here is this plot on the bottom right, which actually shows you the trade-off that we get. The x-axis is robustness, the y-axis is consistency. This is the trade-off that we get, one for the other. And the important thing is that we actually prove this is the best trade-off. Every one of these points on the line on this Pareto frontier is the best. We achieve this, and this is the best you could achieve for any of those points. This is exactly the Pareto frontier. And let me wrap up with this slide, just pointing to many other applications of this learning-augmented framework. We have online algorithms for fair division, either in private or public goods. There's mechanisms in strategic settings, in auctions, in this facility location problem, scheduling, online auctions, when you combine strategic and the online aspect of things. And also segueing into the next talk that Fatih is giving, we also recently got some results on distortion in voting. So how to get the trade-off of robustness and consistency in terms of distortion when it comes down to voting rules. Let me thank you and stop here.
Let's unmute and thank our speaker. All right, so Vasilis, there are a few questions on the chat. So maybe you can just read questions and then answer them. There's a question from Yannick about whether if the predictions are based on historical data, then whether people would have an incentive to lie to essentially kind of manipulate the future predictions.
Good. Yeah, that's a very good point. So the assumption is that we separate the two, right? We assume that the data is not necessarily either. You can make two assumptions, which are common in the literature, right? Either you assume that the agents discount future impact to the utility enough where they're not going to strategically think, like 2 years from now, which actually unfortunately happens in practice, right? People reveal their bid, how much they're going to buy, even though, of course, the ad auctions or whatever, they use their behavior, what they click on, what advertisers are willing to pay for things. They use it to figure out reserve prices, right? So in standard auctions, this is an issue, right? You figure out Meyerson's optimal auction is based on reserve prices that are computed based on a prior, that if you assume historical data, the same issue arises, right? So how did you learn this? Why shouldn't I lie to make the designer think that, lower the reserve price or change the reserve price? So this is a valid point. The assumption is that we decouple the two, as all prior work in, assuming priors are either from a different pool of data, not the same agents, or if it's the same agents, that they're not strategically reporting when this data is being collected. But that's a very good question, yes. I mean, it would be interesting. I know that there's some work in ad auctions where people try to think of strategic bidders that anticipate their bids are being used to figure out reserve prices and then how they should behave anticipating that fact.
Then Bill has a question on individual strategy proofness versus, say, group strategy proofness.
Yes, so group strategy proofness is another very natural problem to study. I mean, you can ask any question. So really, the nice thing about this learning augmented framework is you can ask the same question with group strategy proofness. It doesn't have much to do with the actual underlying setting. It's just consider any setting where people have evaluated performance based on a worst case guarantee. You can revisit that setting and try to refine the worst case guarantee by thinking about how the performance would be affected by an appropriate prediction, again, potentially untrusted. But if it comes to this specific, so for this one, we focus, as a lot of prior work has, on just single unilateral deviations, not group deviations at group strategy proofness. There are results, as far as I know, again, in facility location where group deviations are considered. Things, of course, become more restrictive, but yeah.
Bill also has another question. Bill, do you want to ask your next question?
Sure.
Hi, Bill.
Oh, you clicked twice
muted.
again, I think. You're muted again, Bill.
Sure. Can you hear me now?
Yes.
Yes.
So your proposed mechanism uses coordinate-wise median, but
Mhm.
coordinate-wise median changes when you rotate the axes. So would a rotated version produce a different mechanism that has the same guarantees?
Yeah, so the guarantees shouldn't depend on the coordinates, yes. But I guess the choice, I think the important thing is to not decide what the coordinates, how to shift as a function of the bids. That I don't know what would happen if incentives would be maintained. But as long as you fix those a priori, yeah, that should still hold. As long as the choice of coordinates, the way you rotate, is not a function of the bids, you pre-decide this, yeah, the guarantee is agnostic to that.
And the same holds for the previous axis parallel bounding box algorithm as well, right?
Correct, yes.
Yeah,
and that just comes, that's one of the nice things of worst case guarantees, right? The worst case guarantees means over all instances. So in other words, rather than rotating the axis, you could just rotate the points and get whatever instance it is, right? So if it's worst case over all possible instances, it's also true with respect to the ones where you rotate the points rather than the axes.
And I think it's also because you are looking at L2 norm, which is kind of axis independent, right? So
yeah.
Mustafa has a question.
Sure.
Mustafa, do you want to just unmute and ask your question?
Yes, of course. Thank you for giving me this chance. So in this line of research, it's clear for me that the goal is to speed up algorithms by machine learning predictions. So now I was wondering about what if we took the perspective of trustworthy machine learning, or what if the goal is to compute a social choice function or computing a voting mechanism, but rather than being restricted on combinatorial domain, maybe that we wish to utilize data to achieve fairness or voting mechanisms. So I wonder whether you have any thoughts or ideas about that line of research, whether it is explored or not.
Yeah, so if I understand correctly, first of all, just it's to the first part of the question, it's not necessarily speeding up. This is one of the things people care about, runtime, but it's also online. For online algorithms is what's the competitive ratio. So here we saw what's the approximation ratio. The last paper I have on this slide is about what's the distortion. So this is just any kind of worst case performance evaluation measure that's been used. So you can just revisit this. And again, I want to use the term refine this, because now we're saying I can get that, but also get more caveats, more refined understanding of what I can do. It's not like when we get the best worst case guarantee, it's the end of the story, that now we can actually say, let's get a better understanding beyond that worst case guarantee. But back to your question, I don't know if the last, for instance, paper I have here, which is about voting and saying, what if I have some, I'm trying to get a good candidate in this voting setting, as Fatih is going to talk about later on, you're trying to choose an outcome, choose some candidate that is the best, the efficient choice to make based on people's preferences, but you're lacking how much information you're seeing. You're only seeing ordinal preferences. And the idea is to then use predictions, use kind of background information to try to guide the voting rule toward a better outcome. Fairness is a tricky thing because, the moment you use priors and, you're biasing things in a particular way. So, you want to be careful whenever you're trying to optimize for fairness, whether that bias, because by design, to hope for any consistency, you need to bias yourself in favor toward the prediction, right? You're essentially saying, I'm going to trust the prediction a little bit. If that prediction is misguided, that's a very interesting direction, actually, to figure out how to maintain fairness, how to trust it, and then make sure you don't, that bias you're introducing is not hurting more than it's benefiting. So when it comes to algorithmic fairness, where bias is, of course, the main thing people are trying to avoid, this is introducing bias, which is desirable in many settings, but in others, it's not. So I think understanding the extent of the bias, maybe even measuring it and trying to optimize subject constraints on the bias would be a very interesting direction toward that.
Okay, thank you so much.
You're welcome.
All right, that's the end of the question answer period for this talk. So let's thank Vasilis once again.
Thank you.
All right, let me pause. All right, welcome back, everyone. Hope you had a good coffee break. And we are now ready for our second talk, which is by Fatih Kızılkaya. And he's going to talk about plurality veto and beyond. It's based on a number of papers that he has had recently. And one of them was the ICHKAI 22 distinguished paper, received the ICHKAI 22 distinguished paper award. So looking forward to the talk. Fatih, the floor is yours.
Thank you. Thanks for the nice introduction. Let me share my screen. Okay, is it working? Okay, cool. Okay, let me start right away. So today I'll be giving a talk on natural and practical voting rules with optimal metric distortion that we came up recently. So loosely speaking, this means that these voting rules are optimal in reflecting voters' opinions about the candidates. So I'll begin by explaining what metric distortion means. So I'll be using an analogical toy problem to do that. Suppose that we have 3 islands like this, and then these 4 ships arrive, and suppose that these ships want to collectively decide on one of the islands to meet there. But the problem is that these ships cannot tell the exact distances between themselves and these islands. They can only make comparisons between them. So, for example, if we name the islands as A, B, and C, each ship is able to rank them from closest to farthest. For example, the ship on the left is closest to A, then B, and C. So these rankings are the input of our problem, and the output is one of the islands. And the objective is simply to minimize the total distance that these ships travel. So the motivation here for this problem is that, like, if we think of these islands as candidates in an election, then notice that voters ran across the same problem as these ships. Because if we ask a voter, like, how much do you like this candidate? It's not very easy to answer this question numerically in a meaningful way. So the best, it's much easier for a voter to compare it with some other candidate. So to make things a bit more concrete, let us now first think about this simple question. Is it possible to select the optimal island without knowing the actual distances? So this shouldn't be possible, right? Let me give a simple example. So consider this election with 2 candidates, A and B. And since the rankings are like symmetric, we can assume without loss of generality that candidate A wins. Now, suppose that these are the actual distances. which could have been the actual distances, right? Because one of the ships is closer to B and the other is, let's say, slightly closer to A. Then the cost of candidate A is 1 + 1/2, which is 3/2. But like if we knew the actual distances, we could have done 3 times better, right? By choosing candidate B instead. So we would have a cost of 1/2, which is 3 times better. And this ratio in the worst case among all possible metric spaces, that is for all possible distance functions that you can define between these voters and candidates, which was defined by Anslevich et al. In 2015. And as you can see from this example, it's not possible to beat distortion 3. So the next natural question to ask is whether there exists a voting rule with distortion at most 3. So this question was first posed by Anslevich et al. In 2015. They established the lower bound of 3, which I just showed you. And they showed that Compliant rules comes close by achieving distortion 5. And they also conjectured that the rank pairs rule achieves distortion 3, but this conjecture was disproven by Gol et al. In 2017. They disproved the conjecture by giving a lower bound of 5 for the rank pairs rule. And indeed, David Kempes strengthened this lower bound to square root of m. And 2 years later, Mungala and Wang came up with the first improvement. They gave a novel voting rule which achieved distortion approximately 4.2. But more importantly, they gave sufficient conditions for achieving the bound of 3. And finally, like in 2020, Gkatzelis et al. Showed that these sufficient conditions can be satisfied. In this way, they showed that achieving distortion 3 is possible. But interestingly, their proof is non-constructive, and the voting rule itself is like a complicated brute force algorithm, which I will explain now. But first, here are some well-known voting rules and their distortion. So as you can see, in order to beat the barrier of 5, researchers came up with like novel new voting rules, which is exciting. So first, I'll be explaining plurality matching, which is the first rule that that was shown to achieve distortion 3. Then I'll explain OR voting rules, which are called plurality veto and simultaneous plurality veto, which also achieves distortion 3, but in a much simpler way and more suitable for practice. So plurality matching, the voting rule by Gkatzelis et al. Is based on this notion called the domination graph of candidate C, which is a bipartite graph between voters and voters. So domination graph of candidate C contains an edge from voter V to V prime if and only if voter V ranks candidate C higher than the top choice of V prime. So for example, here the top choice of V prime is candidate A, and voter V ranks C higher than A. So there exists an edge between them in the domination graph of candidate C. For example, this edge doesn't exist in the domination graph of candidate B. That is, we have a different bipartite graph for each candidate. And the reason we care about these graphs is that if a candidate has a perfect matching in his domination graph, then we know that that candidate has distortion at most 3, which was shown independently by Mungala and Wang, Kempe, and Gkatzelis et al. So the accomplishment of Gkatzelis et al. Was showing that there always exists such a candidate. That's a candidate whose domination graph admits a perfect matching. But as I explained earlier, their proof was non-constructive. So the voting rule itself, which they call plurality matching, simply finds such a candidate by brute force. That is, like it constructs the domination graph for each candidate and checks whether they have a perfect matching, and it is guaranteed that at least one of them admits a perfect matching. Here's our voting rule instead, which is much simpler, and it's called plurality veto. So it has two stages, the first of which is plurality voting, that is each candidate starts with a score equals to his number of first place votes, which is also called a plurality score, you know. And then in the second stage, these scores are gradually decreased and a candidate drops out when his score reaches 0. And here's how scores are decreased. One after the other, voters decrement the score of their bottom choice among standing candidates, and the last standing candidate wins the election. Now I will run plurality veto using an example. So first, each voter sends out a vote to their top choice, their most favorite candidate. So each candidate ends up with as many votes as their plurality score. That is the number of voters who rank that candidate at the top. Then we pick an arbitrary voter, let's say the red one, whose bottom choice is C. So red takes back a vote of candidate C, and C gets eliminated because his score reaches 0. Now suppose that we pick the purple voter as the next one, whose bottom choice is also candidate C, but C already got eliminated. So purple takes back a vote of candidate A instead, which is her next bottom choice, right? So A also gets eliminated. So at this point, we know that candidate B will win because there is no other candidate left. But let's go until the end, because I want you to see that at the end of this process, each voter gets matched with the top choice of some other voter, like this. And all of these edges exist in the domination graph of the winning candidate, which is candidate B here. So the takeaway here is that plurality veto implicitly constructs a perfect matching for the domination graph of the winning candidate. So it achieves optimal distortion of 3. So even though this voting rule is very simple, and it also has like a very intuitive, simple proof that it achieves optimal distortion, but it has some issues with adoption in practice. As you may have noticed, like the order of voters changes the outcome, which we wouldn't like in practice, right? Because the voting rule is not anonymous. That is, it doesn't treat voters equally. So actually, plurality matching, the first discovered voting rule with optimal metric distortion, is anonymous, but that one is not neutral. That is, it doesn't treat candidates equally. And secondly, plurality veto insists on picking a single winner, even for elections with obvious ties. For example, here, one of the orderings of voters returns candidate A and the other returns candidate B. But it's obvious that A and B should be declared as tied winners, right? And lastly, a candidate may never win plurality veto, even though he admits a perfect matching. For example, here, one of the orderings returns candidate A and the other returns candidate C. But actually, B also has a perfect matching, but it cannot ever win. And actually, in this election, you know, B seems like a favorable candidate to win because it's the second top choice of every voter, but it cannot ever win. So if we look more closely, what's happening here the perfect matching that plurality veto constructs is actually exactly the same perfect matching M for both of these orderings in both of these elections. And indeed, candidate B in the below, in the election at the bottom, admits the same perfect matching M as well. So the main issue seems to be that like plurality veto picks a candidate based on a perfect matching M that it constructs, but maybe some other candidates admit the same matching M as well. So here, if we think of this perfect matching M as a witness, as a certificate for winning, then it makes sense to declare all of these candidates who admits M as tied winners. And indeed, we need to have a definition of ties because as shown by Smith and Moulin independently, no voting rule without ties can be both anonymous and neutral. And indeed, this definition of ties also makes a lot of sense in the metric distortion setting because we show that for any perfect matching M, the set of winners tied at M is COMEX for every embedding of voters and candidates into a metric space for which COMEX is defined. So the motivation here is that, like, suppose that these candidates on the boundary are declared as tied winners, then like the candidates inside their COMEX hall should be also declared as tied winners, right? Because in metric distortion setting, the goal is to pick a candidate in the middle, in the center as much as possible. Just like imagine that you are surrounded with candidates that are declared as tied winners, but you are not. Like this shouldn't be fair, right? So in order to satisfy this definition of ties, we just need to make a small change in plurality veto. So we don't eliminate a candidate right away when its score reaches 0, but only if there is still a voter who opposes him. That is, like there is still a voter who didn't use his vote, and she ranks this candidate at the bottom. And in this way, actually, plurality veto characterizes all candidates who admits a perfect matching. And by that, I mean every candidate who admits a perfect matching is a winner under plurality veto for some ordering of voters. So in this way, we consider all possible candidates who admits a perfect matching. Now, note that the winner still depends on the ordering of voters, but now at least we have a good definition of ties, which is necessary, as I mentioned, to get the anonymous and neutral voting rule. And also now we are considering all candidates who admits a perfect matching. They are all possible winners for some ordering. So in order to make this rule anonymous and neutral, all we need to do is to run this rule simultaneously for all voters at the same time, which we call simultaneous plurality veto. So just as in plurality veto, every candidate is initially alive and starts with a score equal to his number of first place votes. Then all voters are processed simultaneously in continuous time. From time 0 to 1, every voter, starting from her bottom choice, instantly eliminates those with score 0 and moves on to her next bottom choice. And when a voter arrives at a candidate with positive score, she decrements his weight continuously at rate 1. And the winners are candidates who are not eliminated until time 1. So at this point, I would like to note that there is a voting rule called veto by consumption proposed by Ionovsky and Kondratev for picking a candidate from the proportional veto core, which is like a classical notion in social choice theory introduced by Moulin in the 80s. And this voting rule, veto by consumption, is essentially the same algorithm as simultaneous plurality veto, but with different initial weights, like same initial weight for each candidate instead of plurality scores. So actually there's a deep connection between these like domination graphs, plurality veto, and veto core and metric distortion setting, but I will not go into that in this talk due to lack of time. Before I finish, let me summarize our results for simultaneous plurality veto. So this rule achieves optimal metric distortion of 3 because it picks a candidate who admits a perfect matching in the domination graph. Moreover, this voting rule is anonymous and neutral. And as I mentioned earlier, any voting rule which is anonymous and neutral should also allow for tied outcomes. So another important axiom that our voting rule satisfies is resolvability. That is, every tie can be broken in favor of any winner W by adding just one new voter whose top choice is W. And also recall that we have this convexity property, that is every tie corresponds to a convex set in the underlying space. So like ties corresponds to like a cohesive set of candidates in this underlying matrix space of opinions. And also this rule satisfies many other axioms that people care about in practice. Thanks for coming to my talk, and I can answer if you have any questions now.
All right, let's unmute and thank Fatih. All right, so Fatih, there are a number of questions on chat, starting with, I guess, Dominic, your question. Do you want to ask about
Yeah, so you had a
plurality?
slide where it said that probability matching is not neutral. In what sense did you mean that?
So there might be multiple candidates who admits a perfect matching in their domination graph, right? And plurality matching just like picks one of them arbitrarily. So it doesn't treat candidates equally. It makes an arbitrary choice. So because of that, it's not neutral.
Right, so choosing all of the candidates that have a perfect matching in the domination graph would be anonymous and neutral, I suppose.
Yep, but then you might have a very large set of tied winners. Like you might not be able to resolve them easily. So that's another problem that you would run into if you have done that.
Mm-hmm. Can I ask a follow-up question? So you say this would be a large set of winners. So I guess simultaneous probability veto will then select the smaller set of winners. Have you sort of looked at empirically in simulations how big?
Empirically, almost like it always have a unique winner. So like this resolvability axiom kind of like loosely implies that, right? Because when you just one new voter, it resolves that tied outcome. So as the number of voters increases, like loosely speaking, the number of tied winners should be low. Yeah, but like you can also study this like more formally, I guess, which we haven't done yet.
Okay. Nisarg was asking, I think Nisarg has to leave, so I'll take over the Q&A. He asks, so one could define the rule taking the union over all voter orderings of plurality veto, right? And that way make plurality veto anonymous. I suppose that again runs into this issue of having too many winners, but have you thought about sort of the time complexity of implementing that?
You mean like running plurality veto for all possible orderings of voters and returning all of them? Yeah, that would be actually like exactly same as returning all candidates who admits a perfect matching. It runs into the same issue again. It doesn't satisfy resolvability. Yeah, so satisfying anonymity and neutrality at the same time is trivial. Like if you just want to do that, but like that doesn't seem to be what you would want in practice. Like you want to have few tied outcomes as possible, because like then like you could just return all of the candidates and like it would be neutral and anonymous anyway.
Klaus, you have a question?
Yeah, I have a question. You motivated your talk by, in a metric setting, the axioms you state at the end, are they on the universal domain, or are you using some domain restriction on profiles?
We do not have a restriction on the domain because like when you are embedding these voters and candidates into a metric space, like you can arbitrarily choose which candidate you rank higher if the distances are the same. So like all elections
That's
can
true. No, that makes sense. Yeah.
Space.
Mm-hmm.
You can put all of them into the same.
Okay, yeah, that makes sense. Mm-hmm.
Thank you.
Yeah.
Any other questions? I have several more questions. So this rule satisfies many axioms. Is there any sort of open question of the type, a particularly attractive axiom, is it compatible with a nice rule that satisfies distortion 3?
So like the most desirable axiom that like simultaneous plurality veto doesn't satisfy is, I think, Pareto property. But you can actually satisfy Pareto property by just removing all candidates that are Pareto dominated, and you would still have at least one winning candidate. But then you lose the convexity property because like you removed some of the candidates. So one open question is like whether you can satisfy 3 of them, like convexity, Pareto property, and optimal distortion at the same time. Yeah. So it's like there are some other axioms that obviously plurality, simultaneous plurality veto doesn't satisfy. For example, like Condorcet consistency, electoral consistency. Yeah, I don't know whether those are compatible with like optimal metric distortion, to be honest.
Okay, thank you. If no one has any other questions, then I suggest another round of applause for Fatih.
Thanks a lot.
Thank you. And we'll see each other next time in December, on the 14th of December, at our usual time, the exact same time as today. If I email you with any other times, disregard. It's the same as today. And we'll then hear from Alexandros Psoumas and from Paul Goetz. So until then, see you.